Hey, look at that. How'd it go? Tacos all done. Lena, you got paper here, and everyone picked up the ideal gas law worksheet. Worksheet for today. I know that sometimes it's hard to see when there's other stuff out. Please pick up the worksheet for today. That's classwork that we're gonna get to. Let's return to our workbook and please get out your calculators because woohoo, it's a math class. It's a math class. We are back to learning. We're gonna add to our knowledge of gas laws. First one being one of my favorites because it gets really freaky. It's really freaky. That's probably why I like it. Is Dalton's law of partial pressures. Dalton's law of partial pressures. Put a diagram in here. Notice the plus signs. So we're adding all this up and then it equals the air. This is kilopascals, kPa. So very simple formula for Dalton's law of partial pressures. And that is basically the total pressure is equal to all the partial pressures. So this is what it means, partial, it's just part. All the parts added together equal the total. So partial pressures, add them all up and you get the total. Now the dot, dot, dot means you can go for a whole bunch, like on the previous slide. So this would be this plus this plus this plus this plus this equals that. So you can have a whole bunch. You can have as little as just 2 for your partial pressures. So a typical question, I don't know if it's typical, but this is a typical general question, not a typical question for you. It's asking for the partial pressure of oxygen if the partial pressure of carbon dioxide is 0.7 atmosphere and the partial pressure of nitrogen is 0.12 atmospheres, and they give you the total pressure. So it's just a plug and a chug. That's your total. They give you the total. They give you 0.70 atmospheres, 0.12 atmospheres, and they're asking for the partial pressure of oxygen. Now, the only thing students really screw up with a question like this is decimal places. All of these happen to have the same number of decimal places, but remember when you're adding and subtracting, sig figs go with the least number of decimal places. But all these have 2. You can't drop decimal places. You can't add to decimal places, right? You go with the least number from the ones you're adding together. So what do you guys get for this? I'm sorry? 0.15 atm. So that's the partial pressure of the oxygen. Make sense? Do the next one. Tell me what you get. Not about sig figs, it's about decimal places. How many decimal places will you have? Anyone? 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 Yeah. Yep. 91.8 kilopascals, kPa. 91.8. Notice this says a gas is collected over water. Gas is collected over water. We talked about this earlier, and then that video we watched, they were collecting gas over water. Remember, what was that? You know, are you on your phone? Are you texting? No? Okay. What was that movie we watched, guys? It wasn't a movie, it was a video clip. They collected gas over water. The cable show. Two dudes, stoichiometry. They were going to see if they could blow up a toilet. Yes. Thank you. Was it the toilet that gave that away?
Yeah.
Okay. So you can save these for later. Pretty basic practice. Another topic, if in biology, you should have discussed diffusion ad nauseum, diffusion of particles through a semi-permeable membrane. Remember that, guys? Moving from a high concentration to a low concentration. And all your embedded proteins, your channel proteins in the membrane. Remember diffusion? Okay, well, particles move from a high concentration to a low concentration. Like perfume, if you're right up next to the bottle, it smells more than if you're across the room. So movement from high concentration to a low concentration. A fusion is the movement of gases from a high pressure to a low pressure. So this is chemistry. This is a fusion. But what's different about this and this is this little hole, right? That little hole. So this is showing you the fusion's up top and a fusion's on the bottom, that little hole. High pressure to a low pressure. So if we look, there is Graham's law of a fusion, and this is for rate. This is for rate. So rate has to do with speed or time, right? It becomes a rate as soon as you divide by time. Now, if we just look at straight up a fusion, and we just talk about just gases effusing, going through a little hole, the larger the gas, this isn't the actual gas molecule, the larger the gas, I'll say particle, the slower it diffuses. So this is just in general. Larger the gas particle, the slower it diffuses. I remember that, I don't remember never mind. Just remember that. Larger the gas, the slower it diffuses. So what does it mean for a smaller particle? Smaller particles move faster. Does that make sense? Smaller particles can effuse faster. But if we ask for the rate, like how much faster, you're going to use this law. And that what you want to look at, and that it's rate of effusion for gas 1, rate of effusion for gas 2. Well, you're going to take the square root of the molecular weight of 2 divided by the square root of the molecular weight of 1. So students sometimes forget the formula that you're literally just flipping them. You want to put your second gas comparison over your first. So then if we follow it, the rate of helium versus the rate of nitrogen, that's going to be the molecular weight of nitrogen divided by the molecular weight of helium. And nitrogen is 14.01, but there's 2 of them. So this is 28, it should be 0.02. And helium the molar mass of helium is 4 or 4.00 in our case. So what's 28 divided by 4? You get 7, and then take the square root. This is the formula to take the square root of both, but it's way easier to do your math first and then take the square root. Now notice what it says. Therefore, helium effuses, so you had helium up top. Helium effuses 2.7 times as fast as nitrogen. That makes sense to everyone? So if we look at our practice, what about helium versus neon? So helium versus neon, you're going to do the square root of the molar mass of what over the square root of the molar mass of what? Neon over helium. So on the periodic table, neon is 20.18 molar mass, and helium is, we just said, 4.00 molar mass. So then you get the square root of 20.18 divided by 4. And then take the square root of 5.45. No. 0. What do you guys get? 2.25. Now, what is the sentence here?
Helium diffuses that much faster, that many times faster.
Then right. So when you write it, it's helium or the one on the bottom. Diffuses 2.25 times neon. Yes. I'm sorry. It doesn't matter. It doesn't matter. You could have done the other one on top, but then you would say, yeah. What you do want to, well, the sentence would be a little different if you put something else on top. Not as much. What you do want to do is go with the larger one on top. Larger one on top. Why? Makes your math way easier. Makes your math way easier. Now, here, the rate of effusion of a gas, it's directly proportional to its molar mass, right? The bigger it is, the slower it is, the smaller it is, the faster it is. You should already know this. Gases diffuse from high concentration to a low concentration. Diffusion ability through a small opening. In other words, lighter gases spread faster than heavier gases. So focus on the question. If I just ask you which one's going to be faster, if I just ask which one will effuse faster, you just look at the molar mass and you'll say carbon because it's only 12 and this is 70, right? And if I say how much faster, then you have to use this guy, right? But if I'm just asking which one's faster, it's totally based on size. Make sense? Yeah, cool. Avogadro's law. Now, we didn't cover this earlier because this implies open system. And I'll tell you why. Remember Avogadro? He's that Avogadro number dude, right? He's all about the mole. So Avogadro's law states that the volume of a gas is directly proportional to the number of moles. Now, N is traditionally used called quantity. Quantity. So volume versus over quantity is directly related. It's called Avogadro's law when you're dealing with moles. There are other relationships. Obviously, we could deal with grams, right? But it would be a different relationship. So mole will take into account the type of gas that it is. Does this make sense? So it's a law, but this would be an open system if you have two different quantities, right? Where's the gas particles coming from? So this is kind of an open system. That's why this is kept a little separate, but we're going to use this relationship to explore the ideal gas law. So here's our N. Any questions on Avogadro's law? It's pretty intuitive, right? You add more gas into a balloon, it gets bigger. Yes or no? You got to give me some feedback. Okay. So we're coming up to what's called an ideal gas. And this picture compares, these two pictures compares ideal versus real gases. And ideal gases, we want to assume, or we imagine them to be, or in theory, this is theoretical, in theory, there's no attraction or repulsion between these particles, between gas particles. No attraction or repulsion. What I'm talking about is those intermolecular forces. So that is the dipole, that's the H bond, which is a really strong dipole, and van der Waals. Now remember, van der Waals were just from electron orbiting, right? Just from electron orbiting. And we know that in actual gases, yeah, sometimes the particles are really far apart, but there are times when they're closer together, and we do know they have electrons, and we do know that they would be subjected to van der Waals, but this is so tiny and fleeting that we can imagine a gas if it's not. So these forces, as they do exist, but it's like to the nano measurement of forces. It's so freaking small that we kind of just forget about, like the mass of the electron, right? We don't add up the mass of an electron normally when we're talking about atoms because it's just so freaking small. An ideal gas, we don't consider the forces, even though we know they exist, just because those forces are so small and so fleeting. Does that make sense? And an ideal gas, we also ignore any energy transfer from collisions. Now, if you were to run into a wooden fence full speed with your body, you run into the wooden fence, as soon as you slam into that fence, you transfer some energy and the fence will move, the fence will vibrate. Where'd that come from? It came from you, kinetic energy, and you transferred it. Now, with gases, this collision, we're going to say that the kinetic energy from bumping in is none is lost from bumping in to the surface. Versus if you run full speed into a brick wall, the brick wall is not going to give, right? So that energy that you converted into a wooden fence, a lot easier to run full speed into a wooden fence, you don't get as hurt, is then shoved right back at you, and now you have bruises or a busted nose or something because you ran full force into a fence. Does that make sense to you guys? So with gases, we're just going to say that no kinetic energy is converted to other forms. So this collision in an ideal gas loses no energy. That collision in an ideal gas loses no energy, but we know it actually does. But again, it's so small. And the last assumption, so it's actually like 1, 2, and 3. 1, 2, and 3 is that the actual particle itself, an actual molecule itself, like for, I don't know, fluorine F2, this diatomic, that there's actually no volume to the molecule itself. So, and then we do know that there is volume to molecules. We do know that matter has mass and takes up space. But in ideal gas law, we're going to assume that it doesn't, that it's not even there. So why do we do these three assumptions? One, it will help us predict how real gases work. Exactly? No, not exactly, but it'll be off by something really small. No attraction or repulsion. This is like 10 to the negative 9. Loss of energy from collisions. This is like 10 to the negative 9. Talking about the mass of 2 or 3 or 4 atoms, right? That's like 10 to the negative 20, right? Something really, this is super duper small amounts, right? All independent assumptions, independent events, you multiply, right? So this guy is getting way astronomically small. So if we want to calculate an ideal gas law using theory to predict how a real gas will behave, we can, because mathematically, yes, we're off, but we're off by such a small amount that it still makes the ideal gas law useful. Yes or no? Okay. There it is, PIVNERT, not pervert, PIVNERT. Just rolls off the tongue. What does P stand for? Pressure. But we're going to limit pressure to atmospheres and kilopascals, just in this class. Just for this formula in this class. Volume, you're going to want always in liters. What's temperature in? Kelvin, required. Here is moles, thanks to Avogadro. Look, right, the relationship. Here is mole. And that leaves us with R. R is called the ideal gas constant. And there are several of them. The ideal gas constant. But the two that we're going to use are based on the units. And you will need to change which one you're using based on the units. The ideal gas constant is 0.0821. And that is atmospheres times liter divided by moles times Kelvin. Yes, one number has 4 units. That is one ideal gas constant. The other ideal gas constant is 8.314, but that's kilopascals times liter per mole times Kelvin. And this number has 4. So this is 2 gas constants. So you have to make everything else match. Your liters and your Kelvin, you have to make match. And if you're given atmospheres, you're going to want to use this one. If you're given kilopascals, you want to use this one. If you're not given pressure, you can use either one you want. You can use either one you want. Kind of cool, right? So do we want to get started? Try one? Woohoo, yes, please. This is awesome. This is so much fun. Let's find out how gases are going to behave. How many moles of gas does it take to occupy 120 liters at a pressure of 2.3 atmospheres and a temperature of 340? Actually, let's go back to this guy. Let's just review just a little bit of, and I'll even change color. I just because there were some, come here. There were a little difficulty, some algebra difficulties. If I'm solving for pressure, pressure, what's my formula? It's nRT over V, right? Is that easy to everyone? If I'm solving for volume, It's nRT over P. If I'm solving for moles, it's PV over, anyone? RT. Cool. If I'm solving for T, it's PV over NR. If I'm solving for R, it's PV, pressure and volume. Look at that, pressure, volume over NT. Look at that, mole Kelvin. Pressure, volume, mole Kelvin. Pressure, volume, mole Kelvin. Pressure, volume, mole Kelvin. Solving for R. So don't forget just some basic algebra, how to rearrange around the equal sign when you do these. Because you guys missed some problems on your homework and it was algebra, you know, and that's just, you know, you don't use it every single day, but you will use it in this unit. So it's asking for moles. So that means it's N. I'm solving for N. So N will be PV over RT. It gives me atmosphere, so that tells me what R I'm using, right? It gives me volume. And temperature is already converted to Kelvin. So this is just a plug and chug. 2.3 ATM. Volume 120 liters. Well, over, what's the R for atmosphere? 0.0821. Remember, that's atmosphere, liter, mole, Kelvin. And then my temperature is 340 Kelvin. Now notice what happens with crossing these guys out. My atmosphere is over atmosphere, so that goes away. My liter is over liter, so that goes away. And my Kelvin is over Kelvin, so that goes away. So I'm left with mole, and that's what I'm trying to solve for. Right. So the units actually help you quite a bit. Now, in your calculator, I'm going to multiply across, hit equals, divided by this, hit equals, then divided by this. And how many sig figs? 2. What do we get? 9.9 moles, right? 9.9 moles. So you have been given a worksheet that you picked up. Everyone looking at that worksheet. For number 1, how many sig figs are in your answer? 1. For number 2, write that off to the side. 1. Maybe how about right next to the number 1, right? 1 sig fig. For number 2, how many sig figs? 2, right? You do this before you convert. So 87 degrees Celsius and 31 liters is also 2. How many sig figs for number 3? 1. 4? 1. Preceding zeros don't count. So 0.009 atmosphere is only 1. What about 5? 2. Who said 1? Why do you think for number 5 there's only 1 sig fig?
5. Yeah, 5 is 6.
Okay, for 6? 1. For 7? Look at 900K, it's only 1. For 7, what about 8? 1. 9? 2. So the 97, it's before you add 273 to it. 10, 2, 11, and 12. 2. Okay, so that is from the numbers before you change it. And then, would you please rearrange the formula for each one? So for number 1, it's T equals PV over NR, right? Because it's asking you what's the temperature. Temperature's always in Kelvin. Temperature's always in Kelvin. So for the first one, what R are you going to use? 0.0821. What about for number 2? 8.314. For number 3, you can use either one, right? Because it's asking you for pressure. So nRT, whichever one you use, if you use one, you'll get kilopascals per units. If you use another, you'll get atmosphere per units because it's asking for pressure. Does this make sense to you guys? Okay, you want to knock this puppy out. And when you hand me this, I hand you your homework. Otherwise known as gas worksheet number 2. And ask any questions if you have questions.